All right, so in class yesterday, our little abbreviated class, we talked about the mechanism of electrophilic aromatic substitution. And the example that I gave you was bromination. So there's three steps in this reaction. First, we make a strong electrophile, this iron bromide complex. Then we add the electrophile to the benzene ring, and we break aromaticity of the benzene ring. But that's okay because the ion that we form, the rhenium ion, is resonance stabilized. So one exercise I would give you is try, if you can, and draw the resonance structures of that ion that make it more stable. And then the third and final step is we eliminate the hydrogen that's over here, and we regenerate aromaticity, and the side products from that are HBr from that hydrogen and that bromine, and FeBr3, iron 3 bromide. That's our catalyst there. I also told you that the reaction works with chlorine, but not with fluorine or iodine. So what I want to do first is go through a more, not an abbreviated mechanism, but a mechanism in the way you might draw it, say, on an exam, for chlorine using this slightly different metal reagent, aluminum chloride. Okay, so the overall reaction that we've got is benzene is being treated with Cl2 diatomic chlorine and AlCl3 aluminum chloride. The product that we're going to get is a substitution, not an elimination. You get that. So, the mechanism for this, the first thing we'll do is take Cl2 and an electron pair on the chlorine is going to attack the aluminum of our aluminum trichloride. That creates this complex, which is analogous to the iron bromide complex that we saw earlier. And because this compound has been formed, this chlorine atom is super electronegative. It's electronegative. Well, it is electronegative. Electrophilic, that's what I should have said. Super electrophilic. It's electrophilic enough to be attacked by the benzene ring. So that's what we're going to do. There's our explicitly drawn hydrogen that's going to end up getting substituted. So the bond that we're going to form going to be between that carbon and the chlorine. Electrons are going to come from the bond, from that pi bond, and then the electrons between this chlorine-chlorine bond are going to go here. Okay, so this is going to be our rhenium ion intermediate. So we've formed the bond to the chlorine. We've got a positive charge. And what we've got left from our aluminum chloride reagent is that. So we've created our strong electrophile. That's the first step. Then we've added the electrophile and broken aromaticity. That's the second step. The third step is to eliminate hydrogen and regenerate. aromaticity. So we're going to do that by eliminating HCl, hydrogen chloride. So we're going to form a bond between hydrogen and chlorine. Those electrons are going to come from there. And at the same time, those electrons in the CH bond are going to come down and reform that aromaticity. So we've substituted the hydrogen for a chlorine, and our side products here are going to be HCl, and we'll regenerate the aluminum chloride catalyst. So exactly the same mechanism as with bromination. It's just we're replacing bromine with chlorine and iron with aluminum. Same charges, same arrows, same side products even. Okay, so I spoke in class a little bit about the different classes of EAS reactions. Let's see, that's here. So halogenation, that's what we've talked about so far. There's sulfonation, nitration, alkylation, acylation, and these are all just installing slightly different functional groups onto the benzene ring. But they're all going to work by that same mechanism with those 3 steps: generating the strong electrophile, adding the electrophile and breaking aromaticity, eliminating hydrogen, and regenerating aromaticity. So the only other one that I will expect you to be able to draw the mechanism for is the alkylation. So I'm going to put an M here on halogenation. You need the mechanism for that one, and alkylation as well. Now, as I said, the mechanism is the same. It's just a slightly different electrophile. But to avoid confusing you with a bunch of different electrophiles, we're just going to stick with those 2 classes for the mechanisms. Okay, but anyway, we need to talk about sulfonation next. All right. So I mentioned that SO3H group, which you may or may not have seen before. So what does that SO3H mean? Well, it's kind of like having sulfuric acid attached to your molecule. And, maybe not too surprisingly, the way you make a sulfonated benzene ring like this is by treating it with fuming sulfuric acid, and the fuming part here means that we're actually using SO3, sulfur trioxide, dissolved in concentrated sulfuric acid. So that's a particularly nasty mixture. I don't like working with it, nor should you. But occasionally it's important to do a reaction like this. Now, one of the convenient, well, sometimes this is convenient, sometimes it's not, about this reaction is it is reversible. So if you take the sulfonated aryl group, or benzene ring, and you treat it with dilute sulfuric acid, you'll actually just take the group off. And so, of course, this can be sort of annoying, because if you treat this with water, or let this contact water, that'll create a small amount of dilute sulfuric acid, and you'll just decompose your molecule. The advantage of that is if you want to install a group on your molecule in order to do some other chemistry, and then you want to remove that group, this is an effective reaction for doing that. So that's sulfonation. Arguably a more important reaction is nitration. So in the same way, sulfonation attaches a sulfonate group, nitration attaches a nitro group. So we start with benzene, react it with nitric acid and sulfuric acid. And we get nitrobenzene. So as a reminder, this is what the drawn out structure of the nitro group looks like. It's a bit odd. It's got a positive and a negative charge, but it's overall neutral. In this case, the active electrophile that actually reacts with the benzene ring is this. This is called a nitronium ion. There's another particularly interesting advantage of this reaction, and that is that we can do some extra chemistry with the nitro group. And specifically, we can reduce the nitro group to an amine. So we go from NO2 to NH2. The reagents that we need for that are zinc and hydrochloric acid, and then in a second step, sodium hydroxide. So this molecule is aniline. And the nice thing about aniline is we can do a lot more reactions with it than we can with nitrobenzene. We can substitute this nitrogen with things. And it just gives us the opportunity to select between whether we want a nitro group on our molecule or an amine on our molecule. So that's nitration. We're going to use that pretty significantly in the upcoming sections. Okay, we've talked about halogenation, sulfonation, nitration, and now we're going to talk about alkylation and acylation. So these two reactions actually have specific names, and they're called Friedel-Crafts. So this is the Friedel-Crafts alkylation that we'll start with. And as I mentioned, the mechanisms for all of these reactions are basically the same. And in addition, the reagents for the Friedel-Crafts alkylation and acylation are quite similar to the ones we used for the halogenation. So let me show you what that looks like. Instead of a diatomic halogen, we're going to use an alkyl halide. So this is 2-chloropentane. And like the halogenation reactions, we need a metal catalyst. And so if we're using an alkyl chloride, we're going to use aluminum chloride, AlCl3, just like we did for halogenation. And the product that we're going to get is not chlorination of the benzene ring, but alkylation. So we're going to attach this alkyl group, this 5-membered chain, to the ring. So if we want to draw a mechanism for this reaction, it's very similar to that of chlorination or bromination, in the same way that in the halogenation reactions, the electrophilicity of the halogen is increased by the metal catalyst. The electrophilicity of the alkyl group, or the carbon fragment, is increased by the metal. Okay, so how does that work? So we'll start with our alkyl halide, and we have AlCl3, our metal catalyst. We're going to, just like we did with halogenation, make a bond to that metal. So we've got this. Chlorine has a positive charge here. And now we're going to show explicitly the formation of the carbon electrophile. And so what we'll do is take the electrons from this carbon-chlorine bond and move them back up to the chlorine. So we're going to break that CCl bond. And that's going to generate a carbocation. Now we know that carbocations are electron poor, and so they're going to be good electrophiles. So what happens to our carbocation? We'll take our benzene ring with our explicitly drawn hydrogen. There's our carbocation. And we're going to form a bond between one of the benzene carbons and the carbocation carbon. So we'll show that like that. Of course, you want to be really careful here about how many carbons you put on. So there's 1, 2, 3, 4, 5 carbons. All right, and we've also got a positive charge down here. And then, just like we did with halogenation, our aluminum chloride reagent is going to come in take that hydrogen away, and then the electrons are going to come down, regenerate aromaticity, and so the products of that reaction are an alkylated benzene, hence Friedel-Crafts alkylation. And like the halogenation reactions, we get the hydrogen halide, hydrogen chloride in this case, and we get our catalyst back at the end of the reaction. So that's awesome. We've formed a carbon-carbon bond. Those tend to be kind of tricky to make in organic chemistry, and so we, as chemists, try to look for carbon-carbon bond-forming reactions whenever we possibly can. But this one has a caveat, of course. Couldn't be that easy. And that has to do with this. So this carbocation is fairly happy But what if we were to generate, say, a primary carbocation in the course of trying to do this reaction that has the possibility to rearrange to form a more stable carbocation? If that can happen, it will. So one thing we need to do is watch out for carbocation rearrangements. So let's do, well, we've done an example with chlorine. Let's do an example with bromine as our halogen. It doesn't really matter. Okay, so this is bromopropane, or propyl bromide, whatever you want to call it. And our catalyst is iron 3 bromide. So what is the product of this reaction going to be? Well, you might initially say, oh, I know, we're just going to take this alkyl group and put it on the benzene ring. So maybe we get, now you can tell from my sarcasm that I'm drawing the wrong thing, but you might initially think, oh, we're going to get that, right? We just stick the group on there. Well, no. That is not the product that's going to form. So let's explain why that's the case. And we'll also practice drawing the mechanism because you can't get enough practice doing mechanisms. Okay, so we'll start with our alkyl halide. So there's bromopropane, and we're going to generate a complex. There we go. With the iron 3 bromide. Like that. And then, like we did up here, we're going to break the carbon-halogen bond and generate a carbocation. So this carbon-bromine bond right here, those electrons are just going to go and hang out on the bromine. So from that we get the iron species, and then most importantly we get this carbocation. Now this is a primary carbocation, which is not happy. It's generally speaking pretty unstable, and you don't want to form these things. It's okay in this particular case because we can do a rearrangement. So I'll explicitly draw this hydrogen because that's the hydrogen that's going to move and fix our problem with the primary carbocation. And so this bond is just going to instead scoot over to that electron deficient carbon atom. That hydrogen that we drew out specifically is now sitting on that carbon, and now we've got our positive charge on this carbon atom. And so that's a secondary carbocation, which I won't give it a full happy face, I'll give it sort of a partial happy face, because a tertiary would be even better, but we can't do that in this particular case, so we'll have to settle with a secondary, and that's all right. Okay, so now this is the electrophile that's going to react with the benzene ring, and that's going to give us a product that's different than this straight chain alkane. All right, so let's do that. So there's benzene. And so we're going to use this carbocation, which looks like that. So, excuse me. I knew all this talking was going to get to me. All right. So we form a bond between these two carbon atoms. Go like that. Here's our rhenium ion intermediate. And now let's look very closely at the attachment pattern of our carbon atoms. So we are connecting to that central carbon, which has 2 methyl groups on it. So we're going to form this bond to the central carbon rather than to one of the carbons on the end. And now our positive charge, I guess my voice is going to be like this, isn't it? All right. And then the positive charge is going to be on that carbon on the ring. Okay, and as we've done previously, we need to eliminate hydrogen and regenerate the aromaticity. So this is conveniently drawn right here where I need it, actually. So we're going to use the iron bromide from this previous step, which is still hanging around. Going to form a bond here to make HBr. And these electrons are going to come down, satisfy the positive charge, and regenerate our aromaticity. Okay, so you'll notice that the product that we've drawn is distinctly different from what I proposed that we might generate. And so the reason we have an isopropyl group, right, we still got the same number of carbons, 1, 2, 3, 1, 2, 3, but the attachment point is different, and that's because of this carbocation rearrangement. So this is the really important step that you need to watch out for. So what is that going to look like when you're actually doing problems? Well, you're going to want to look at the alkyl halide that you're starting with and say, all right, if I were to just pull this bromine off and make a carbocation that looks like that, is it going to rearrange? If it's primary and you've got other stuff attached to it, yeah, it's going to rearrange. And so you just have to sort of look at that analytically each time you do a Friedel-Crafts alkylation to determine if you're going to have rearrangement. And eventually it'll become second nature, but make sure that you work out each problem individually as you're getting used to it. Okay, so it's nice that we can do this chemistry. And we can make molecules like this. That's great. But what if we did want to make that? How do we do that? Well, that's going to be the Friedel-Crafts acylation. Okay, so this was the Friedel-Crafts alkylation. So let's move on and do its sister reaction. Let's see, that was page 4. This is page 5. Okay. Sister reaction, the Friedel-Crafts acylation. So okay, alkylation and acylation are similar but different words, all right? So let's remind ourselves the difference between those two. So that is an alkyl group, just carbons. An acyl group has a ketone, or really a carbonyl of any sort, usually a ketone. So make sure you have that distinction down pat, because this is actually going to affect the products of the reaction. Okay, well, actually, we were trying to make this molecule. So why don't we go ahead and do that with a Friedel-Crafts acylation. All right. Oh. Everyone say hi to my dad who just texted me. Hi, Dr. Eubanks Sr. Okay, so for AlCl3, for the Friedel-Crafts acylation, we're going to use, instead of an alkyl halide, we're going to use an acyl halide. All right, so really it's the same thing where you've just got carbons attached to a halogen. In this case, we always use chlorine. If you use bromine, it's okay. But in the laboratory, you would always use a chlorine derivative. But just with a carbonyl here. So another name for this is an acid chloride or an acid halide, because these are kind of related to carboxylic acids. Anyway, so the product of this reaction, and watch closely here for the connectivity of the carbon atoms, is that. Okay, so I was just going on for like half an hour about this whole carbocation rearrangement thing and how you can't make this molecule. Well, right, keep it in your brain for a second. 3 carbons in a row. Look at that. We've made a something attached to a benzene ring with 3 carbons in a row. And so that's the power of the Friedel-Crafts acylation, is you don't get a carbocation rearrangement. So let's look briefly at what the mechanism is going to look like for this one, not because I necessarily want you to be able to draw it, but because I want you to understand why we don't get a carbocation rearrangement, or at least sort of at the surface level. So there's our acyl halide. Here is our aluminum trichloride. And we're just going to do the same thing that we've been doing. Hopefully this will start to get boring at some point, once you get used to it. So Cl, AlCl3, positive charge, negative charge. Okay, so we formed a complex with the aluminum, or the iron if it's bromine, like we've been doing in all of these examples. And we're actually, from this point, we're going to continue doing the same thing that we have been doing. So we're going to break the carbon-chlorine bond. Those electrons are going to go onto the chlorine. We're going to make that side product. And then this is where things may look a little bit different. The carbon fragment that's left over is that. So it's just like a carbocation, except we've got a carbonyl on it. And this is called an acylium ion, right? Acyl, acylium. And the power of the acylium ion is that they do not rearrange. Yay. Because the resonance stabilization with that oxygen atom makes these quite a bit more stable ions than just the regular carbocations. Okay, so now if we really wanted, we can finish off the rest of the reaction. There's our acylium ion. Going to form a bond to it. Again, this should be looking familiar by this point. Okay, making sure we get the correct connectivity there. And then this keeps being very convenient how I draw the metal catalyst right next to it. Of course, that's dangerous. If you don't end up having this ClAlCl3 thing next to this molecule when it's time to do the elimination, you'll need to draw it again, of course. But our product for that reaction is going to be that nice straight chain ketone or acyl group that we were originally hoping to get on the last page. Okay, so we're not really. I just said that, but that's a lie because what I actually wanted to make was this, just the alkyl group. I don't want the ketone. Fortunately, there's an excellent reaction that we can use to get rid of it, and that is called the Clemmensen reduction. So, all right, so we take our ketone, we treat it with a zinc amalgam, which is just an alloy of zinc and mercury. And then we use some acid and some heat. And that just replaces the carbonyl with a CH2 group. And in effect, it just gets rid of the carbonyl. All right, so now we've made the actual straight chain propylbenzene that we were hoping to get in the beginning. Okay, so that concludes the list of important EAS reactions. What we need to do now is talk about what happens when we try to do these reactions, but the benzene ring that we're doing the reaction on already has something there. Okay, so what happens when we don't just have one group that we're dealing with, because that's nice, but often we need to create molecules that have a lot more complex functionality than just a mono-substituted benzene ring like we've been looking at. And the way we're going to do that or rationalize the different arrangements of products that we're going to get are by using activating groups and deactivating groups. So we'll start with activating groups. And activating groups, as the name suggests, activate the ring. They make the aromatic ring slightly more reactive. That's actually not the most important thing that they do, though. Generally speaking, activating groups are electron donating groups. Okay, so let's explain this. This is probably best explained with an example. So let's say that we take toluene, methylbenzene, and we do a nitration reaction. So we're going to use HNO3 and H2SO4. Sorry, drink break. Okay, so we're going to nitrate toluene. So we've got three possible isomers that we can get from this reaction. Okay. Hopefully you can pause the video and identify these with their designations. But these are ortho, meta, and para. And these form in a bit of an interesting ratio. Ortho 63% for this particular reaction. Meta would just get 3%, essentially nothing. And para 34%. Suspiciously looks like roughly half of 63. And that's not a coincidence. So there's two different ortho positions, here and here. And there's just one para position there across the ring from the methyl group. And so what this data tells us is that essentially when you have a group like a methyl group, or in this case, it's an activating group, when you've got an activating group already on your benzene ring and you do a reaction to it, doesn't matter what sort of EAS reaction we do here, but whatever substituent we install is going to be selectively added to either the ortho or para position in essentially equal preference, except we've got two ortho positions and one para position. And we're essentially not going to get any significant quantity of meta substituted product. The reason for that is that the ortho and para arenium ions, so that's that intermediate when the actual reaction is occurring, they have a resonance structure that's extra stabilized, so a really low energy resonance structure. And so that means that that really low energy resonance structure is a bigger contributor to the overall molecule's reactivity. And that means that the ortho and para products form in greater amounts. So most activating groups are ortho, para directors, is what we call them. So if we have an activating group, like a methyl group, on our aromatic ring, that is going to direct other groups. All right, this is important. It doesn't have to do with where this group ends up, but the activating group directs other groups, in this case, the nitro group that we're adding in the nitration, to the ortho or para positions. Okay, so if we have activating groups, you might not be too surprised to find that we also have deactivating groups. In the same way that activating groups are electron donating, deactivating groups tend to be electron withdrawing. Okay, so let's do another example. In this case, our deactivating group is going to be a nitrile, a CN. And what the heck, let's do the same reaction. Let's do a nitration. And I don't think you'll be too surprised to find that ortho, ortho and para are favored by activating groups. Well, guess what? Meta is going to be favored by deactivating groups. All right, so the ortho-meta-para distribution for these, for this reaction is even more extreme. 6% ortho, just 1% para, and 93% meta. So very selective reaction. And so this ends up being really for the same reason. In the case of activating groups, the ortho and para rhenium ions have a resonance structure that's extra stabilized. In this case, the meta rhenium ion has a resonance structure that's more stabilized. So most deactivating groups are meta directors. Okay, as with all rules in chemistry, there's got to be an exception, and there is an exception, and that is the halogens. So all right, so halogens are deactivating groups. They're electron withdrawing groups. Mostly just inductively, so it's not a very strong effect, but they are deactivating groups. However, we would expect them to be meta-directors, right? Because deactivating groups are meta-directors. Well, wrong. These are ortho-para-directors. All right. So, oh, darn it, I just realized I have forgotten my little chart of activating and deactivating groups. So I will see you on the screen recording in just a moment.
All right, so if you go on to the Blackboard page, you will find under Extra Resources, there's this chart of directing groups. So if you look in here, you'll see that we've got a list of a whole bunch of different types of groups that you might have on the benzene ring. So in this case, the benzene ring is here off to the left-hand side of each of these groups. And so at the top, we've got the most strongly activating groups. So those are our electron donating groups. And these are all ortho-para directors. So if these are attached to a benzene ring and we do an EAS reaction on that benzene ring, these groups are going to cause that new incoming substituent to be at the ortho or para position. In the middle here, we've got a hydrogen, which is just nothing. And so that doesn't really have an effect. And then we've got that weird exception where the halogens are deactivating groups. They're electron withdrawing groups, but they're also ortho-para directors. So again, down here at the bottom, we've got the deactivating groups, and these go sort of in increasing order of strength. So nitro being the most strongly deactivating group. And these are all also electron withdrawing groups, but importantly, these are meta-directors. So if these are attached to a benzene ring and we do an EAS reaction on that benzene ring, the new incoming substituent is going to preferably be installed at the meta position. So have this chart with you when you're working problems. You'll also have this chart available on the exam. So you don't need to memorize this, but you do need to familiarize yourself with it. All right, so I will see you in lecture on Tuesday, and we'll finish up a little bit more information on directing groups, and then we'll do some practice problems with, of course, with directing groups, and then also with synthesis. I know synthesis is a scary word, but once you get to know the reactions really well, hopefully the synthesis will come a bit more naturally. All right, thank you guys for putting up with me being sick. I'm sorry. Hopefully I will be back to 100% by Tuesday and we can get ready for the exam, which is not this coming Tuesday, but the Tuesday after fall break. All right, thanks.